Okay. Hello? Okay. So let's start. So the first, just an FYI, the first homework assignment should be out today. You basically have, I believe, 3 parts. 2 parts are kind of, a little bit theoretical, and 1 part is you have to write a code. Okay? So you have 2 weeks up until Monday, basically, 2 weeks from now. So start looking at the assignment now. That's my recommendation. Don't delay yourself. TA office hours, I believe, are going to be announced on Piazza, so you're more than welcome to talk to the TAs. And again, start working on the assignments a little bit earlier, right? Make sure you have grade scope account, because that's going to be your submission, and that's how you're going to get your first homework assignment. A couple of other things is that for your homework, please use LaTeX to generate your answers. For those of you who don't know how to use LaTeX, you have to learn very quickly how to use LaTeX. So every submission should be made in PDF format. And also, you're going to be submitting your code. Okay? And then 2 weeks down the road, we're going to get the second assignment. Okay, so today we're going to start talking about function approximation. First, I wanted to talk about Monte Carlo tree search, but I think that we'll talk about Monte Carlo tree search a little bit later in class, because I just want to make sure that we start getting into deep learning part, which is something that you will need to know for your second homework assignment. Okay? And as a reminder, you have 7 penalty days for the homeworks. But please use those days wisely, okay? So that in the future you don't run into the situation where you have to come to me and say, look, I have to go to the conference or I have an interview and I've already used my 7 days. That's not going to be an excuse, okay? So 7 days is more than enough for you to plan ahead for whenever you're going to be away. So please don't come to me with, can I get an extension because I have midterm and I've used all my penalty days, okay? And the penalty, I guess, for being late is 10%, so that's pretty significant. A number of students in the last class actually have gotten A- or B+ because of the late days, even though they've done well in the course. So please plan ahead. Okay, so today we're going to look at function approximation. And we're going to start looking at the large-scale reinforcement learning. So reinforcement learning can be used to solve large problems, right? So for example, if you look at the backgammon game, you have 10 to the 20 states. If you look at the Go, you have 10 to the 170 states. That's a huge number of possible states. Or think about, controlling a helicopter. You basically have a continuous state space. So discretizing the state space into bins will obviously introduce some discretization error. And it's not, it's very difficult to deal with just discretizing the continuous space. So how can we scale up model-free methods for prediction and control? So what we're going to do is we're obviously going to be using something that's called value function approximation. So far, we've looked at representing our value function via the lookup table, right? So every state S has an entry V sub S. And every state action pair, SA, has an entry QSA, right? And that's what we've been doing so far. So these are, traditional reinforcement learning methods. Everything is discrete, and we assign value for every single state or every single state value entry. And obviously, the problem with the large-scale MDPs is that there is just too many states or too many actions to store in memory. And it's also very slow to learn the value of each state individually, right? Particularly if you have a very large state space. So the solution for large-scale MDPs is pretty simple one, right? We're going to be estimating the value function with a function approximation. So we're going to be saying that we're going to be introducing some value function, which is going to be a function of some parameter w that's going to be approximating our value function. Okay, so we're going to be building a parameterized model of our value function. Now, what we're doing here is we're introducing certain inductive biases, right? And the inductive biases is that if the state S and S prime are very close to each other, according to some distance metric, then the value function should be close to each other as well, right? And as we go through the learning, we'll start, seeing that is the case. Now, the parameters W here are going to be learned by, our RL objectives, right? So effectively, and again, you can think of it as some kind of introducing inductive bias or a compression mechanism that basically has, some notion of proximity, right? If two states are similar to each other, you expect the value function to be similar to each other as well, right? Obviously, if you're in a situation where if I observe a particular state, my value function is 1, and if my state changes by a little bit and my value function changes a lot, so you have very discontinuous functions or very sort of high curvature functions, then it's going to be more difficult to learn them, right? But generally, that's not the case in practice. The same thing for Q function. We're going to be approximating our Q function with some parameters W by some parametric function. And the other key idea here is we're going to be able to generalize from seen states to unseen states, right? And again, this is where inductive bias comes into play, which is you might observe a new state that you've never seen at the training time, but if this new state is close to some of the previous states that you've seen at the training time, then obviously you can generalize, right? So that's the idea of using function approximations. And obviously you'll see later in sort of deep reinforcement learning, most of these function approximators are going to be multi-layer perceptrons or multi-layer convolutional networks and such, right? So for the value function approximation, we're going to be replacing the table with a general parameterized form, right? So the state comes in, you have some parameters, some differentiable function, and it outputs the value of the state, okay? You can also construct the settings where the input to this black box or whatever the function is the state and the action, and you're producing the Q function. Okay? The output is going to be the Q value for the state and the action. And how do you design these parametric functions is sort of up to you, right? We're going to look at some examples of that. So there are many function approximators, right? So for example, you can use linear combination of features. That's a very popular approach that works pretty well in practice, particularly if you know what are the right features to use. Neural networks, which is something that we're going to spend most of our time in this class. You can also use decision trees. You can also use nearest neighbors, Fourier wavelet basis. So there's a whole bunch of different function approximators that you can use, right? So it's up to you to design what these things are. Now, in this class, we're going to be considering differentiable function approximators, right? So for example, we can look at the linear combination of features, and we can optimize for the weights of the linear combination. And we're also going to be considering neural networks, okay? Let me just step back a little bit and remind you of the gradient descent. So let J sub W be a differentiable function with respect to some parameter vector W. And we're going to be defining our gradients, just for notational purposes, to be the gradient of this objective with respect to weights W, right? And obviously, to find a local optimum of the objective function, we're going to be changing our parameters, in the direction negative to the gradient, right? So delta W is going to take this form, okay? That's a standard gradient descent based algorithms. These are going to be your friends for the rest of the course, because pretty much whatever we're going to be doing in this course, we're going to be doing that, right? Now, if you're interested in sort of optimization for reinforcement learning, there's a whole bunch of different algorithms recently introduced, but generally gradient descent, stochastic gradient descent in particular, is sort of the easiest and to some extent is the best performing algorithm. And there's a hyperparameter that you have to choose. You have to choose the step size. Okay. Now, within the stochastic gradient descent method, we're going to be trying to find parameters minimizing the mean squared error between the true value function and its approximation. So one way to set up the problem is we can say, well, if we know the true value function and we have its approximation, one thing we can do is we can just look at the mean squared error, right? We can just look at the expectation of pi, this is our policy, of the true value function minus our approximation, okay? And the gradient basically, if you take the gradient of this objective function with respect to parameters w, you end up having this expression, right? This has come from the first term, and here you take the gradient of this value function, which is your approximation with respect to parameters w. Now, there is something tricky in this particular formulation, right? And we'll come back to this, is in general, you don't know what the value of the function is, right? If somebody told you what the true value of the function was, then this is just now becomes almost like a supervised learning algorithm, right? I'm trying to estimate the value function, somebody tells me what the true value function is, and I'm just doing regression, okay? So we'll come back to that later. This would be the instance of supervised learning. That's exactly how you train your standard, let's say, neural networks or convolutional neural networks. This is your prediction, this is your target, and you're just trying to minimize mean squared error. Now, in the case of stochastic gradient descent, you basically get samples of the gradient, right? So you pick a sample, a particular value of the state, and you just optimize that. And we'll come back to SGD in this class. One thing to point out, just like in stochastic gradient descent, the expected value is equal to the full gradient update, right? So that's why we can use stochastic gradient descent. Precisely because if I take an expectation of this quantity, it will give me the correct gradient. So on average, I'm going to be moving in the right direction by doing sort of these stochastic gradient descent steps. Okay, so now let's think about how do we represent the state. Okay? So one of the common approach for representing the states is to use feature vectors, or to represent the state using feature vectors. In fact, for a lot of papers, you'll probably see that for domain-specific applications, in many cases, you might know what the right features to use. For example, you might parameterize your state according to the distance of an agent from some landmarks. Or, I don't know, you might look at the piece and pawn configuration in chess, right? So you're basically saying, if I'm in this configuration, maybe my feature is 1. Maybe you're going to parameterize by the trends in the stock market. Right? Stock market goes down, your robot is not going to get a good reward, right? Let's say. So there are many things that you can do when coming up with a feature representation. Now, in sort of this class, we're going to avoid this particular setting, and we're going to start saying, well, can we actually learn what the right features are? But it's important for you to know that you can also construct, specific hand-engineered features, especially if you have some domain knowledge about your problem. Okay? So let's look at one example. Very simple example, which is a linear value function approximation. So what we're going to say is we're going to represent the value function by a linear combination of features. So we can construct a whole bunch of different features that we believe are useful for our representation of encoding in terms of encoding the state. And we're going to say that our value function, our approximation, is going to be given by some linear combination of our features, hand-engineered features. Okay? And there are n of them. The objective function just becomes the quadratic in the parameters w. Okay? In this case, if I look at the gradient descent, the update rule becomes fairly simple, right? You just take the gradient, and you can say that the update here equals to the step size, something you have to choose. Prediction error is basically how off your prediction from the correct target, times the feature value, the magnitude of the feature. If you look at this, you should start realizing this is like a least square estimation, right? This is just a linear regression problem, right? If you know the true value of the state, this is just a regression problem. In fact, if I gave you the true value of the state, I could solve this problem just using least square estimation, right? There is an optimal solution. It's a convex problem. I can just find you the optimal features, right? So in practice, a number of people actually, especially practitioners, like this particular approach because it's simple. There's an optimal solution. Or if you're doing it via the gradient descent because you have a lot of data, then you can just do gradient descent on it, and it's convex, it's stable. You don't run into sort of any issues optimizing it. Okay. Now, so far, when we looked at these settings, right? And again, this is a least square estimation problem. Very simple. So when we look at these problems that I've mentioned before, we're assuming that the true value function is given by some supervisor, or there's some signal that's telling us what's the true value function. And the interesting thing about reinforcement learning is there's no supervision, right? You're only getting rewards. And that's the power of reinforcement learning, but also kind of its disadvantage. And in practice, what we're going to be doing is we're going to be substituting a target for the true value of the function, right? So for example, if we're doing Monte Carlo approach, we're taking Monte Carlo approach, then the target is the return G sub t, right? So what does that mean? That basically means if I start at a particular state, S sub t, and I execute my policy all the way down to the terminal state, it's a stochastic policy, right? So I'm going to be executing all the way down to some state, terminal state. I'm going to get G sub t. That's the reward, right? Obviously, in these settings, G sub t is going to be noisy. So think of it as a noisy estimate of your target, right? Ideally, you'd like to get the expected reward, right? That's what you're trying to optimize, but you're only getting a sample from it. So what that means is that if I start at a particular state S sub t, I simulate an episode, I might get 10 as my reward. If I start simulating again, I might get -1 as the reward, right? So you can obviously see that this is going to be a very noisy estimate of the target. Okay, so that creates some problems for us. Imagine a supervised learning algorithm. Imagine you're trying to train a computer vision task. I give you a dog, and I ask the labeler, what is that? And the labeler says, yeah, I think it's a car, right? You say, okay, I'll update it's a car. And then the next labeler says, yeah, I think it's a dog, right? You update it's a dog. The third labeler says, yeah, I think it's a dog. And then the fourth labeler says, I think it's a shoe, right? So you can see that, when you sort of getting the noisy estimates of the target, it's generally very hard to train these systems. Now, for temporal difference learning, the target is going to be the TD target, right? And that's also the most commonly used one because it's cheaper, computationally cheaper. So your target is the reward at the next time step plus your own estimate of what the value function is, right? So let's look at this particular equation also. A lot of different algorithms like Q networks, deep Q networks, and various variations of it basically have something like this in place, right? Pretty much a lot of different RL algorithms have this particular decomposition, right? So what are they doing? They're basically saying, well, if I'm in a particular state, I execute the action. Do I get reward in the next time step? That's the signal. That's the true signal you're getting, right? If you're getting a good signal, then you can learn. But let's say you typically have very sparse rewards. So if at the next time step you don't get any signal, so the reward is 0, then you're basically trying to match these two, right? And what is this? This is basically nothing, right? It's like no one is telling you what the next state should be. It's almost like you're relying on your own prediction to estimate your own prediction, right? Which is very bizarre, if you think about it, but there is nothing else you can do about it. Right? So reinforcement learning, there is nothing magical in reinforcement learning, right? At the end of the day, your true signal comes in rewards. And if your rewards are sparse, it's going to take you a very long time to learn, right? If I tell you, your reward is like, there was an example, I think in one of our first classes, like, try to take a series of actions such that your PhD thesis gets the best PhD thesis award at CMU, right? I mean, that's kind of a sparse reward, right? You like do it for 5 years and then you didn't get the thesis. I say, well, that's -10. Let's try do it again, right? So obviously you can see that there is this connection here. So when people talk about reinforcement learning are basically not working, or optimization is hard, or it's sensitive to the hyperparameters and everything, a lot of it really comes down to what the structure of your reward, what your reward structure is, right? So in many cases, sometimes people sort of do the combination of both, where instead of just looking at the next time step, you do TDN, where you unroll it for n time steps, hoping that you will see some reward as you're unrolling it, right? Obviously, it becomes more computation expensive, but at the same time, you might get some signal out of it as well. Noisy signal, but at least some signal. And later on in the class, you will see that when we look at this update equation, right, there is nothing in this equation saying that this should be a linear system. This could be a multi-layer perceptron. This could be a convolutional neural network parameterized by parameters W, right? And that's the objective. So let's look at the Monte Carlo for function approximation. So the return G sub t is unbiased, which is good. That means that on average, as you repeat this procedure many, many times, if I start at the particular state S sub t, and I just do it millions of forward unrolls, eventually if I average over those, I'll get the correct G sub t, right? So in expectation, it's expensive, but I'm going to get it. And in many cases, like if you look at Monte Carlo tree search algorithms, they're essentially trying to do that. They're essentially trying to unroll your system all the way to the end and basically see what kind of feedback you get in parallel. So in principle, you can apply supervised learning to the training data, right? Because you're in particular state S, you unroll the systems to some terminal state, you look at your reward, and that's your signal. Right? You take a new state, you unroll it, and that's your signal. Now, this is a noisy signal, right? So maybe you want to do multiple unrolls, some unrolls in parallel, to get some estimate of G sub t, right? And obviously, you can see that if your state space is large, then you sort of have to figure out, what state space to choose. Do you randomly choose the states and so forth? So in this case, for example, using linear Monte Carlo policy evaluation, you basically do the update using this update rule, right? Or in principle, if the capital T here is fixed and you're looking at the linear system, then you can just solve it using least square estimation problem, right? It's a supervised learning problem. You have it even though your signal is noisy, your targets are noisy, but the optimal solution exists there for the linear case, right? And the Monte Carlo converges to some local optimum. So let's look at the Monte Carlo with value function approximation. This is the algorithm, precise algorithm. So input the policy pi to be evaluated, right? So you have some policy. And it's a differentiable function v tilde. You can think of it as not necessarily linear. It could be non-linear. It could be a neural network or whatever your function approximation is, as long as it's differentiable, because we have to be able to compute the derivatives of the value function with respect to our parameters w. Okay? So initial value function weights theta. They can be set up to 0, and you basically repeat forever. You can generate an episode. So you start at a particular state, take an action, go to the next state, get an action, go to the next state, and so forth, using your existing policy pi, and then just update your parameters using this equation, right? This is prediction error. That's the derivative with respect to parameters theta. And you just generate a new episode, you update the parameters, generate a new episode, update the parameters, and such. Okay? And obviously, you can update the parameters as you go from t-1 to 0, right? So because you're visiting all of these states, you might as well update them because you have them. Now, the TD target is a biased sample of the true value, right? Obviously, it's a biased one, but you can still construct sort of a supervised learning to this training data, right? You have a state. You take an action according to your policy pi, you get the next state, and you just compute the reward plus your approximation to the next state of the value function to the next state, right? So in principle, you can construct your own data set like this and just do supervised learning, right? And as I mentioned before, you have to be very careful, because if most of these rewards are 0, then you don't really have a target signal, right? So you're kind of just basically saying, well, I don't know what the reward is, so whatever my prediction should just be discounted value at the next time step. Okay? So for example, if you're using linear TD learning, right, then you basically have alpha, this is your delta, this is your prediction accuracy, times the features themselves, whatever features you've designed, the linear features. Yes?
Yeah, so the TD learning is used by a sample. Does it mean that there's the guarantee that you converge to the true, right?
So in many cases, if your system is nonlinear, if your value function approximation is nonlinear, then there's no global solution, right? If the system is linear, I don't think there is a particular guarantee. Under certain conditions, I think that as you sort of repeat this procedure infinitely many times, you will converge to the local optimum. So there are certain, if you're interested about convergence guarantees of all of these different algorithms, you should look at the book. Under certain conditions, these algorithms will converge. So it's not like they're going to be like oscillating. The question is how good of a value they're converging to depends on specifics of, and the assumptions you're making on what these things are. But this is, yes?
In the previous slide, the gradient, should it also not have the next slide?
The next slide, sir?
Yeah, for the TD learning. Yeah, the gradient update, should it also not have v hat s prime comma w?
We had, what do you mean, like here?
No, the chord that's being multiplied.
This one?
Yeah, this chord.
Should it have what?
The gradient with respect to v hat s prime comma w as well.
So this is the gradient of v hat with respect to w, with respect to the parameters.
Yeah, so because the reward also has s prime as well, right?
No, the reward doesn't have S prime. The reward is basically saying once you take an action, you go to the next state, then you get just the reward. What's the reward at being at that state?
The approximation given by our model, which is also a parameter of w.
So right now we're working with the model-free methods, right? We're not basically, right now we're working with the model-free methods. There is no sort of explicit probability of the next state given the previous state and the action. If you're working with the model-based methods, you know what the transition probability is, then you can take an expectation with respect to the R and get that as your signal. Right now, we're working with the model-free methods. So there is no sort of dependence on S prime here for the reward. Yep. Oh, I see. So you mean like, why don't we take the derivative of this term? Yeah. This is a good question. We'll come back to that. You don't take the derivative with respect to this term. Right now, you can think of it as basically saying, this is your target, and this is fixed target. Right? And what we're doing is we're updating this term here. That's our prediction. It's a good question because now, sorry, I misunderstood your question. I thought you were asking like, is R is a function of S prime? But that's a very good question. Why don't we take derivatives with respect to this guy? Because it's a function of W, right? So the way, the short answer here is that we're treating this as a target, right? Because if we start changing both the target and the prediction, then things become very unstable. In many cases, what ends up happening is that you fix the target, and sometimes this would call the target network. The target network doesn't change as much. This is changing frequently. And then once in a while, you resync what your local prediction model does with what the target prediction model does. So once in a while, you're kind of bringing them together. Otherwise, if you start changing this term to match this term, but you're also changing this term, then it becomes a weird learning rule, right? Imagine that I change my prediction and my target is changing, and I'm changing my prediction, my target is changing, right? So you have to fix this term. But that's a very good question. Later on, I think that once we start looking at the deep Q networks, with networks parameterized by neural nets, this problem will become a very, very difficult problem to deal with. Okay? And the specific solutions will allow us to get like a little bit more stable behavior. Okay, so this is the algorithm for TD learning with value function approximation. So let's look at what's happening here. You initialize the value function weights, W, right, it says before. And for each step of the episode, you sample the action, right, according to your policy. You take an action, you observe the reward, and you observe the next state. Okay? And then you're updating your parameters by just looking at the delta times the derivative of your value function with respect to parameters. So if your value function is a neural network or any other differentiable function, you take derivatives with respect to theta here. Right? You update your state and so forth. And then you kind of like go up until you reach some terminal state, and then you again initialize at some other random state. You go up until you reach the terminal state and so forth. Okay? Again, if you look at this particular formulation, this is a very interesting looking formulation, right? You have your prediction, but your own model is being used as the target for matching your prediction, which is very kind of funny thing to do. It's like I give you an image, I run it through the model, and I ask you, what is the correct prediction? And you're saying, I think my own model thinks it's a cat. And you're basically saying, okay, it's a cat, right? So that's effectively what's happening here, right? And that's why the importance of R is important. So sometimes people talk about reinforcement learning as being able to deal with delayed rewards, right? Or sparse reward signals and such. And that's where the problems come. Because if your rewards are very sparse, then you basically don't get any signal. You can also see that much like in tabular methods, right, in discrete state spaces, most of the learning will happen around value functions where you're observing rewards, right? So most of the reinforcement learning algorithms, the way you can think about learning is that certain states have rewards, right? And most of the learning is going to happen around those states because you're seeing whether it's a good state or a bad state. And then eventually through this process, it sort of back propagates to the other states, right? And that's essentially what's happening with these ones, right? So control. So how do we optimize our policy? Once we do policy evaluation for a given pi, right? Once we have our approximation of the Q function, then the policy improvement is pretty simple. We just do epsilon greedy policy improvement, right? We just basically take Q. For any state, we basically say we're going to take the action that maximizes Q. Right now, we're still making assumptions that our action space is discrete, right? So we can always pick the maximum. And with some epsilon probability, we're going to choose any other action. Okay? So once we do that, we have a new policy. We can run, again, the same algorithm, reevaluate our value of the state or the action value function, and then just update the policy again. So the action value function approximation is exactly the same as the value function, right? In many cases, we're going to be working with this parameterization more frequently than just approximating the value function, even though in some cases, there have been a few papers like dueling networks that basically approximate both the value and the Q function. So the value of the state and the Q function, sort of combine them additively. So again, here we can minimize the mean squared error between the true action value and the approximation. And using stochastic gradient descent, we're getting pretty much the same update rules, right? So nothing has changed when we go from the value of the state to the Q function, okay? And the Q function is a function of two parameters, the parameters of state and the action, right? And later on, we'll see how people parameterize Q function. You can use different ways of parameterizing the Q function. Again, if you're representing the state in action by feature vector, notice now your future representation here is a function of state and the action, not just the state, right? Because you're estimating the state action function. And you can also represent action value function by a linear combination of features, exactly the same way, so it's just a copy. And you can use stochastic gradient descent to basically find the solution. Okay? Increment and control. So just like prediction, we basically have to find what the correct target is. And if you look at, for Monte Carlo methods, if you look at the Monte Carlo method, they basically have exact same, equations as we've seen for the value function, right? Very simple. You're basically running the network up until you obtain the reward, and then you take the gradient. For the TD0, for the TD learning, the target value again is RT plus the Q of the next state in action. So that's the Q function. And you change the parameters using this expression here. Okay? If you look at this particular expression, it now becomes very similar to the Q learning, right? In fact, a lot of algorithms like deep Q networks, various variations of it, are basically based on this equation, or variations of this equation, right? So if you look at the papers, that's essentially what you have. And it's a very simple derivation from TD learning. You can extend it to TD, not 0, but TDN, if you want to unroll it for n times steps. You can kind of like combine, again, TD learning with Monte Carlo methods to perhaps improve the accuracy of your model. Again, we run into the same problem as before. This is our prediction. This is our target. So no surprises here, right? We're just expanding it to account for state and action. So let's look at the algorithm, and these algorithms kind of good. You should look at the book as well, because the book is actually doing a really good job at spelling out the code for different algorithms. You'll effectively be implementing something like this for your second homework, a version of this for your second homework. So let's look at this is Sarsa algorithm. This is episodic Sarsa algorithm. So the input is a differentiable function Q. Okay, so it's a function defined on the state and the action. You initialize the value function weights, right? Let's say they can be initialized to 0. S and A is your initial state. So you have initial state and initial action, which you can pick randomly, for example. Initial state and action for the episode. So for example, if your policy is epsilon greedy policy, so you repeat for each step of the episode, you take an action according to your policy. You observe reward and the next state, S prime. If F prime is terminal, so if the state is terminal, then you're updating your parameters, just basically getting what the final reward is. Hopefully you'll get some final reward at the terminal state, minus your prediction, the gradient, right? And then you just basically go to the next episode. You start, again, running a new episode. Or you choose the action as a function of Q tilde, your approximation right now. For example, it's epsilon greedy. Okay? Again, epsilon greedy is, we'll see later that if you kind of like formulate the problem a little bit differently, you don't have to use epsilon greedy. You just can use greedy. Just take the action that maximizes your Q function. And then the update rule takes this form. Right? So in Sarsa, your action is epsilon greedy. In sort of like Q learning, you would just replace this thing by taking the maximum of all possible Q function or Q values. Okay? And then you take gradient with respect to the Q, update the state, update the action. Okay? So this is more like an episodic control algorithm, because you're essentially running the episode as you're running the episode, you updating your function approximation q, right, tilde. Once you have q tilde, you basically have the policy, which could be epsilon greedy policy, right? And as you're running these episodes multiple times, you will converge to some local optimum of the q function. And hence, once you have the q function, you have policy, right? Because you know what actions you should be taking. So here you kind of, you're kind of doing evaluation and control as well. So at the end of the day, you will get some policy out of your q function that to some extent is some local optimum, right? Over here. Any questions? Yes?
Why is it called
It's a good question. I think it's kind of like, well, the terminology is, the book is choosing that particular terminology. I think the reason why is because it's not quite, you're sort of taking the gradients, but your targets are not quite the correct targets, right? So you have this quantity here. So the name, it's not like a gradient descent in the sense of like supervised learning algorithm. It's more like you're doing gradient descent, but your targets are this, given your own estimate. So it's just, there's no particular reason why it's called semi-gradient, basically. But let me show you an example of a mountain car problem. So this is a setting of a minimum time to goal problem. So let's say, you basically have the state, which is the car's position and velocity. Okay, you have action, forward, reverse, or none. You have rewards, which is always -1 until car reaches the goal. Right. So the more, the longer it takes you to reach the goal, the more negative reward you're going to be accumulating. And it's episodic up until, either the episode ends after some number t steps t, or you reach the goal. Right? So obviously what the system needs to learn to do is that basically if you're in this position, you basically do reverse so that the car could go up to here, and then you do forward so that you can reach the hill. So the goal is basically here. I guess it's not really showing where the goal is, but the goal is located here. You basically want to go over the cliff, right? So if you just always push forward, thrust, your car will never reach over the hill. So it has to learn the policy that it basically has to go all the way back and forward to reach the goal state, right? And this is what basically is happening, as you go through the episodes, position, velocity. So it's like, it's basically, if you look at these graphs, it basically learns that if you are in this particular state and your velocity is small, then you need to kind of go backwards, hit thrust, and so that you can go around the goal. So it's a little bit hard to read what these things are, but essentially this is what's happening. If you have a small velocity in your wrong part, you basically have to go back. So after about, in this case, 900 episodes, the model is basically learning what the optimal policy is here. Okay, so here's an example of steps per episode in a log scale. It's a lot of episodes, averaged over 100 runs. So, for each episode, you averaged over 100 runs. And as the number of episodes increases, you basically converge to some value. One thing to note is that if you look at these learning rates alphas, right, when you're optimizing your policy, it's a hyperparameter that you have to choose. And the choice of the hyperparameter can also have an impact on perhaps your final performance, right? Much like you're doing optimization in deep networks, depending on your learning rates and such, you can reach different local optimum. Okay, so let's look at the batch reinforcement learning. So gradient descent is simple and appealing, but it's not very sample efficient. So one thing to do that can help us a little bit is to basically seek to find the best fitting value function, or try to look at the agent's experience. Right? To try to come up with some training data. So let's look at what we can do here. So let's say we're given some value function approximation, right? That's what we have. And we have some experience D consisting of state value pairs. Okay? So for a particular value function pi, we have the training set. And so what we can do, instead of doing gradient descent, as I mentioned before, we can just do least square algorithm. So we're going to find parameter vector minimizing the sum of squared error. And in many cases, if we have a linear policy, as I mentioned before, we can find the optimal value of the parameters without resorting to stochastic gradient descent. We can also do something that's called experience replay. And this is something that, in the future is going to be very suitable for our needs, and something that you will be implementing in your second homework assignment is we're going to be looking at experience consisting of state value pairs, let's say, and we're going to be learning using the following sort of setting. We're going to sample the state and the value from experience randomly. And then we're going to be applying stochastic gradient descent update rule. Okay? So what's the difference compared to the previous ones? It's a very simple idea. In fact, you look at it and you basically would say, why does it even have its own name? Imagine the settings where when you're running your episode, right, what happens is that you're in a particular state, you take an action, you go to the next state. Okay? So you start with S1, you take an action, you go to S2, right? You're starting at S2, you take an action, you go to S3, right? And so forth. And that's how you would generate an episode, T, right? And now if you're doing gradient descent, you're taking the first one, you're updating, you're taking the second one, you're updating, you're taking the third one, you're updating, and so forth. The issue with doing this in general is that S1 and S2 will be very highly correlated, right? Because in many cases, particular state, I take an action, my state is not going to change that much, right? So experience replay is basically a setting where you're saying, well, in fact, I'm going to create my own training set, and I'm just going to be randomizing it. And you'll be surprised how much faster you can train these algorithms, because now there's no correlation between the states, right? It's kind of the idea that imagine you're training a neural network on images. And I first give you 1,000 images of cats, and your model is training. And then I give you 1,000 images of dogs, and the model is training. I give you 1,000 images of trucks, and the model is learning, right? So obviously there's a lot of correlation. Now, asymptotically, as my learning rate is sufficiently small, I'll learn, yeah? There's no particular reason it will not learn. But at the same time, it's a much better to break the correlation. And we'll see that once we start looking at Atari games or open gym environments and such, you will see that this is going to be kind of randomization is very important, so that your states are not correlated. When we think about, and this also becomes very difficult if you have a real robotics applications, right? Because you have a robot and you can still do experience replay by just randomizing it, but it becomes more difficult compared to simulation environments. So, okay, and then later on in class, we're going to look at the deep Q networks. So in deep Q networks, you can think of parameterizing this value function as a deep neural network, as a deep convolutional neural network. And then we're going to be figuring out how to change these parameters, so how to update the parameters of the network. Couple of things that I want to say. So today's class is probably going to be a little bit short, but a couple of things that I want to say. For the next 2 lectures, we're going to look at deep neural networks, and we're going to look at convolutional neural networks. So for those of you who've taken a deep learning class, that's going to be kind of repetition for you. For those of you who haven't, this would be an introduction, a very short introduction into some of the deep learning methods and some of the optimization techniques. So for the next couple of lectures, you're going to be looking at deep learning book and reading relevant material from the deep learning book, because we need to learn a little bit about the value function here and how we're going to be parameterizing, how we're going to be training and stuff like that, right? Because obviously all the techniques, all the optimization techniques that you see in deep learning, including batch normalization, dropouts, momentum, choice of the learning rates, basically more or less translates into this framework as well. Okay? So we need to know how the optimization is carried along in sort of in deep learning for us to be able to train these ones. Right? One big challenge, and again, I would encourage you to look at the book as well. One big challenge for us going forward is going to be, if I can just quickly say a few words, is going to be dealing with this quantity here. Right? And it's going to be dealing with precise question that was asked, how do we make sure that this W is the same as this W? So if I change my prediction W, it's affecting my target. My target is changing as well. If I'm changing my prediction and my target is changing, what does it even mean? Right? How do we make the system more stable? And so there are a few tricks of doing that. A lot of these tricks are kind of more like hacks to make the system be stable, right? But that will be the problem. That's why for a lot of sort of research that you're doing in deep reinforcement learning, and particularly when you try to look at something more complex tasks, you need a lot of compute. And compute is important. Why is it important? Because if you work in the simulation world, if I simulate billions of settings, once in a while I'm going to hit the reward, right? So the more simulations I do, the more chances for me to see the reward, accurate reward. And the better I can do propagation and the better I can do learning, right? So these methods in general are very, very sample inefficient. But it's not surprising. It should come as a no surprise because there is no free lunch, right? It's not like if I don't have enough rewards that I'm shaping throughout my problem, you're basically not giving enough information to your system. And now you start thinking about, okay, can I come up with different objective functions? Something that would allow me to learn these parameters W without actually observing the reward, right? So now there's a lot of work in this space, and we're going to look at some of that work maybe briefly towards the end of the class, where people are saying, well, maybe I can do some kind of unsupervised learning. Maybe I can try to predict what my next state would be. Maybe I can do something else, because obviously kids learn without you know, the way that kids learn is that they kind of walking, they're doing stuff. Once in a while you tell them, no, this is good, this is bad. Once in a while the kid falls and it hurts to get negative rewards, so kind of learning not to do that. But generally there's obviously some other things in place for figuring out what these parameters should be. Okay, so just as a preview for you to think about these methods. Okay, so we're done. So for the next class, your homework is out. It should be out today. Start working on your homework. The next two lectures are going to be Introduction to Deep Learning. If you've taken the class, it's just going to be a background for you.
So would a problem well be result from high